Can you design an LRU cache in O1 per operation? This pattern mastery essential is a must-win in systems-flavored interviews. It proves you can pair a hash map with a doubly linked list to get constant time get/put, and manage eviction policy precisely. Let's build it using basics so your explanation and code are smooth and convincing. Let's break this down. We need a cache with capacity cap. Operations.key returns value or -1, also marks key as most recently used. Put key, value, inserts or updates, moving key to MRU. If size exceeds capacity, evict the least recently used. We want O1 per op. Let's assess. We need two abilities: fast lookup by key, hash map, and fast reordering/eviction at both ends, doubly linked list. The map points key to node. The list stores nodes ordered from MRU, head side, to LRU, tail side. Moving to MRU, remove node and add after head. Eviction. Pop before tail. Complexity is O1 for all modifications. Here is the structure. Design helpers, _add _after _head node, _remove node, _move to _head node, and _pop LRU. Get, if missing return -1, else move node to head and return value. Put, if key exists, update value and move to head, else create node, add to head, and if size exceeds capacity, pop LRU and delete from map. Now let's implement the linked hash map-based LRU cache, taking advantage of its built-in ordering to achieve constant time get and put operations. This elegant solution leverages the fact that linked hash map can maintain items in access order, making LRU behavior almost automatic. Class definition and constructor. We create a class that extends linked hash map so we inherit all the useful map behaviors, but with the ability to customize eviction. We store the maximum number of entries this cache is allowed to hold. The constructor takes the cache capacity from the user. We call the parent constructor with three key settings: initial capacity, load factor, and most importantly, access order equals true. This means each time we get or put, the entry is moved to the end of the internal order, exactly matching LRU behavior. We store the capacity value for later comparisons when evicting. Get operation. When the user tries to retrieve a key, we hand the call off to linked hash map's get or default. If the key doesn't exist, we return -1. Because access order is enabled, this get will also move the accessed entry to the back of the internal list, making it most recently used. Put operation. This inserts or updates a key value pair. If the key already exists, it becomes the most recently used. If it's new, it's added at the tail, again respecting access order. Automatic LRU eviction. This method is the magic behind eviction. Every time put is called, linked hash map asks, should we remove the eldest, least recently used entry? We answer, yes, if the map size has grown beyond its allowed capacity. This instantly removes the oldest entry, the true LRU. And that's how this algorithm works. It first relies on linked hash map to keep elements in access order, then automatically evicts the least recently used entry whenever the capacity is exceeded. Efficient, simple, and elegant. Let's test our LRU cache using these operations. We insert an access keys to confirm that the cache correctly evicts the least recently used items. Add keys 1 and 2. Get 1 returns 1 and makes key 1 the most recently used. Adding key 3 evicts key 2, the LRU. Get 2 returns -1 as expected. Adding key 4 evicts key 1. Final gets return -1, 3, and 4 based on what remains in the cache. And that's exactly what the program outputs. The results match perfectly. So, our implementation is correct. The LRU logic updates and evicts items just as expected. Now let's implement the custom LRU design, combining a hash map with a doubly linked list to fully control eviction order in constant time. We combine a hash map for instant key lookup, a doubly linked list to track usage order, most recent at the tail, least recent at the head. This helper class N represents each cache entry as a node in a doubly linked list. K is the key. V is the value. P is the previous node. N is the next node. We have a default constructor and a constructor that sets key and value. This holds the maximum number of items the cache is allowed to store. This hash map maps each key directly to its node in the linked list. That's how we get O1 access to any cache entry. We create two special nodes. H equals dummy head. T equals dummy tail. They don't store real data, but they simplify list operations at the ends. In the constructor, we set the cache capacity. Then link head and tail so the list starts as H less than, greater than T. Initially, the cache is empty, with only these two dummies. This helper removes a node X from the doubly linked list. It does that by connecting X's previous node directly to X's next node, and vice versa. No search required, since we already have the node reference, 01 time. This helper inserts node X just before the tail T. That position represents the most recently used item. Steps. Get the node currently before T. Link that node to X. Link X to T. Now X becomes the newest, most recently used node. When we get a key, we ask the hash map for its node. If it doesn't exist, return -1. If it does exist, we remove that node from its current position and add it back near the tail, marking it as most recently used. Finally, we return its value. All steps are constant time, map lookup plus 01 list operations. This is where we insert or update cache entries, while also evicting least recently used ones if needed. If the key is already present, we grab its node, update its value, remove it from its current place, and re-add it near the tail. This marks it as most recently used again. If the key is new, we create a new node with the given key and value, put it in the map, and add it to the tail as the most recently used entry. After adding a new key, if the cache size exceeds capacity, we find the least recently used node, that's always HN. The first real node after the dummy head. We remove it from the linked list, and remove its key from the map. This keeps the cache size within the limit, and always evicts the LRU item. And that's how this algorithm works. It first tracks items in a hash map for 01 lookup, then uses a doubly linked list to reorder entries on every access and eviction. Efficient, simple, and elegant. Let's test our LRU cache with this operation sequence. We insert values, access them, and verify that the correct keys get evicted when the cache is full. We store 1,1 and 2,2. Get 1 returns 1 and marks key 1 as most recently used. Inserting 3,3 evicts key 2. Get 2 returns -1, confirming the eviction. Inserting 4,4 evicts key 1. Final get calls correctly return -1, 3, and 4 based on what remains. And that matches the expected output exactly. So, our implementation is correct. The cache maintains proper LRU behavior throughout the test. If you want to show real systems thinking in an interview, the LRU cache is it: constant time lookups, constant time updates, and precise eviction. It proves you can pair the right data structures to hit strict performance targets. Let's do a recap. The task is to design a cache with a fixed capacity that supports 2 operations in 01. Get key returns the value and marks it most recently used. Put key, value, inserts or updates, and if we're over capacity, evicts the least recently used entry. We compared options and landed on the classic pairing: a hash map for instant key lookup, and a doubly linked list to maintain usage order. This combination avoids linear scans and lets us move items to most recent or evict from least recent in constant time. The plan is simple and disciplined. The map stores key node, and the list orders nodes from most recently used at the head to least at the tail. Helpers handle add to head, remove from list, move to head, and pop from tail. Get moves the access node to the head, put updates or inserts, then evicts from the tail if needed. We followed that blueprint exactly, using head/tail sentinels for clean pointer ops, and successfully ran the solution on LeetCode without any errors. We verified behavior through LeetCode runs, accesses updated recency correctly, evictions occurred at capacity, and all test cases passed as expected. The takeaway: great performance comes from the right pairing. Hash map plus doubly linked list gives true 01 for both operations, and shows you can design for speed, order, and correctness all at once.